Hello, today we're going to start talking about similarity, and there is a connection between similarity and dilation, but they're not exactly the same thing. Objects that are dilated are similar, but not all similar objects are dilated, and we're going to kind of look at that throughout today. So our objectives are, students should know the definition of similarity and why dilation alone is not enough to determine similarity. And given two figures, students describe the sequence of a dilation and the congruence that would map one figure onto the other. And so as you look at this very initial image, hopefully you can see that the two shapes look awfully similar, for lack of a better word. And so are they? And we need to describe what it takes to be able to do that. First thing I would point out is that they're not dilations. And how I can know that is if I just connect a few of the points, a dilation should end up, all the points work backwards to the same exact space. And if you start connecting these, you're going to see, and make sure you do the corresponding parts. So that one's here, and then this one is there, and then this one should be here. And you're going to notice that none of them end up lining up at a singular point. And so that matters. But do they look similar? And I would say yes. They seem to be a scaling of one image to the other. So I might say something like, yes, the images look in proportion to one another. But this is not a dilation, as we cannot find our center. And so then it begs to question what exactly is a similar object. And really, it just kind of ties all the way back to this idea of solely understanding, are they in proportion or not? Okay. So a dilation adds that center point. Similarity by itself just needs to have things in proportion. Okay, so we go to the first example. And we see in the picture below we have a triangle ABC that has been dilated from center O by a scale factor of R equals 1/2. It is noted by A prime, B prime, C prime. We also have triangle A double prime, B double prime, C double prime, which is congruent to the triangle A prime, B prime, C prime. And just quick note, there we go. So it asks to describe the sequence that would map triangle A prime, double prime, B double prime, C double prime onto triangle A, B, C. And what they've done here is they've sort of helped set you guys up. By itself, a dilation would need a point. And so, as you can see, if I were to connect A prime B prime to B and C to C prime, they all track backwards towards the origin. Okay? And so if I wanted to move this A double prime, B double prime, C double prime triangle onto A, B, C, you can see that one dilation isn't going to be able to do it if I'm centered around the origin. Okay, so one thing that we could do, because they want us to go A double prime, is we could translate. And so if I translated left and moved A all the way to A, that would be translate left 10 units. Because remember, translation needs a distance and a direction. And down 1 unit. That would get us to triangle A prime, B prime, C prime. And then after that, I have to dilate 2 about the origin. Ooh. Okay, and so that would map one triangle onto the other. So that would get me here to there. Okay, and so you start building out this idea or this concept of similarity is based on, can I sequence transformations to get one object on the other. Now, you might be asking, well, what happens if I didn't choose the origin as a point? It is possible if we connect A to A double prime, B to B double prime, and C to C double prime, that they all sort of hit right around that spot, if that is your value for O. But the bigger picture here is, do you understand what similarity is? And similarity is this ability to list out a few transformations, including a dilation, to go from one object to the next. Okay, notice it can't be congruence. We're not talking solely rigid motions, which is why we have a dilation. Okay, and this next example I think kind of highlights that even better. Triangle ABC was dilated from center O by a scale factor of 1/2. The dilated triangle is noted by A prime, B prime, C prime. Another triangle, A double prime, B double prime, C double prime, is congruent to triangle A prime, B prime, C prime. Describe the dilation followed by a basic rigid motion that would map triangle A prime, B double prime, C double prime onto triangle ABC. And so again, you're trying to work from this triangle here to that triangle there. Okay. And so the idea again is that, is there a sequence? And so as I look at this, I'd have to move again, translate, left 6 and up 2. Okay, so symbols for that would be translate -6, 2 if I was using function notation of triangle A double prime, B double prime, C double prime. Followed by a dilation about the origin with scale factor of 2. And so that would be dilation about the origin 2. Okay. Now, again, is that the only sequence that you could do? No, you can start to reflect. I thought of it in terms of like, what happens if I were to have translated first and looked at it in a dilation, the opposite direction, wherein I had A, let's just call it A triple prime at 6,4. B triple prime at 8,6, C triple prime at 10,2. And what did I do? Well, I scaled out by a factor of 2. And I got my triangle. And then I would have to translate left 12 up 4. And notice the numbers and how they connect back to the ones that I did choose before. I had left 6 and up 2. And now I have left 12 and up 4. And then think about what your scale factor was going from A to A triple prime, B triple prime, C triple prime. And again, the idea is that when you're similar, there's a sequence of motions. I wouldn't say rigid motions any longer, but there's a sequence of transformations or these motions that will bring one object to the other. And do they line up at that point? And you can certainly say that there are. Now, how can we prove that two triangles are similar? Well, really, what we have to do is make sure our scale factor must work for all segments. Okay, so this is how we know if we have a similar shape. All right, so if I'm looking at this and I'm keeping in mind scale factor is image divided by the pre-image, well, then I could look at this in terms of AB primes over AB. Does that equal, question mark, A prime C prime over AC, which does that equal the same thing as B prime C prime over BC. And I warn you, there will be times where you get two of the ratios to be equal, but the third one will not. So you really have to check all three. If you don't, you're setting yourself up for failure. And so if I set this equation up, then I can go back and I can back substitute. So I can find AB. AB is 15 units, and A prime, B prime is 10 units. And then I look for AC, so AC is 18 units, and A prime, C prime is 12 units, and B prime, C prime is 4 units, and 6. And so if I look at each of these can reduce. Both of those have a 5 in them, both of these have a 6 in them, both of those have a 2 in them. Each one of them simplifies to 2/3. And so that's my scale factor. That's how you figure your scale factor out. And can we describe a sequence of rigid motions? Yes. Okay. First thing I would note is that whether the orientation from A to B is the same. So A to B, one is going counterclockwise, and so is the other. So what that does is it takes the reflection off the table. Okay, and then essentially what you have to do is just find a center point that you can dilate from. You could pick any of the vertices, and you can dilate it by 2/3. So let's just say A, about A, comma 2/3, and what that's going to do is it's going to shrink your shape like this. And so here would be like B double prime, C double prime, and then you could match them up. So translate along the vector of A to A prime. So that would move A to A prime, but I'd still end up with a triangle that kind of looks like this, right? And so then I'd have to rotate all the way around so that B ends up on B and C ends up on C. And so the rotation would be about point A of the measure of the angle BA B prime or CA C prime. They're the same because they're vertical, so the measure of angle B prime A prime B triple prime. Okay, so that would be the sequence that you'd work from. And so you can continue doing that for all of these problems. Are the two triangles shown below similar? Again, first thing you want to check out is the ratio of the image over the pre-image. And so I set it up with each of the segments. The question being, are they equal? Okay, so real quick, 10.67 over 6 equals 4 over 3 equals 8 over 6. And so right at the moment, I would say that these two are equal. The problem is I have no idea about this 10.67. So there's a variety of ways you could do this. You could put this in your calculator. You could get equivalent ratios to make sure that they make sense. And so if I turn 10.67 into an improper fraction, or I'd get 32 over 3 divided by 6, which is really the same thing as 32 18ths, which is equal to 16 ninths. And 16 ninths is not the same thing as either one of these two, because that would be 16 twelfths. And so these things are not equivalent and therefore not similar. And so you got to get out this definition. Well, yeah, they look pretty identical, but the true definition is whether they're in proportion. Okay? And so you continue on looking at these. I'll ask you to pause your video for a moment. You can write down the images. But the ratios you're going to compare: 4/12, 8/24 versus 5/15. And hopefully you recognize 4 and 12, 1/3, 8 and 24, 1/3, 5 and 15, 1/3. So my scale factor is 1/3. How can I get these? Again, you can kind of pick and choose, but one example may be a dilation about B of 1/3 followed by a translation along the vector A to A prime. So essentially what I've done is I dilated about B, brought this A double prime here and C double prime there. I match these two things up. These actually look parallel, so I might not have to rotate this, but just in case they're not, so we rotate about A prime, a measure of C prime, A prime, C triple prime, because it would look something like this. So you close that gap up, and then you just reflect over A, C. Okay, so that would give you the sequence that you've been looking for. In the final example, they ask you, again, I'll ask you to pause the video, and you're making a comparison between each of these. But my ratios are 1.2 over 6. Does that equal 2.1 over 10.5? Does that equal 1.5 over 7.5? And so as you're looking at these, you might be wondering, well, how can I handle these without my calculator? Just remind yourself that if you move the decimal place over, it's like multiplying by 10, both top and bottom. And so 12 over 60, does that equal 21 over 105? Does that equal 15 over 75? So this is 1/5, which equals 1/5, which equals 1/5. And so this proves that things are similar. And then all you have to do is really start to think about the sequence. First thing I would make sure I recognized is what is the orientation from A to B. This goes clockwise. Sorry, this is clockwise, where this one is counterclockwise. So that implies I need a reflection, and you can kind of follow the same thing I did up there. Final thing I would ask you to do: pause the video, write down the lesson summary. A similar transformation or similarity is a sequence of finite number of dilations or basic rigid motions. Two figures are similar if there is a similarity transformation taking one figure onto the other. Every similarity can be represented by dilation followed by a congruence. And what they mean by congruence is a rigid motion. Okay, if you're going to summarize this, there's a few things that you want to know. The symbol is just a single squiggly line, and that things must be in proportion. Okay? Thank you for your time.